Leontine Alkema is joining us today from UMass Amherst, where she's an associate professor in the School of Public Health and Health Sciences. Leontine's work focuses on developing statistical models and tools to improve estimates of demographic and health indicators worldwide, particularly in relation to reproductive, maternal, neonatal, and child health. She collaborates with a lot of international groups in the areas of global health and family planning, including the United Nations POP Division, the Guttmacher Institute, and the WHO, among many others. She's going to talk to us today about GOT data, quantifying the contribution of population period-specific information to model-based estimates, and I'm really looking forward to her talk. So whenever you're ready, Leontine, you've got about 40 minutes for your talk, and then we'll leave about 10 minutes for questions. And if people want to, if they need to interrupt, put up your hand and I can interrupt Leontine. Otherwise, we'll keep questions till the end. Okay, thanks very much.
Thank you, Neve. Yes, feel free to interrupt me if you have a clarifying question. Happy to speak to that. Yeah, thanks very much for inviting me to give a talk here at the Conference of Applied Statistics in Ireland. So for a long time, I had the hypothesis that every Irish person was either a statistician themselves or they were married to a statistician. And at some point, I did have to reject that hypothesis after flying Aer Lingus and actually visiting Ireland. But then I replaced that with the hypothesis that Irish statisticians are great to work with, but also really fun and delightful to have a chat with and a drink with. So again, thank you very much for having me at this conference. I'm delighted to be here, but I also hope that once this is in person again, then maybe you can invite me again and then we can actually do the whole having a chat afterwards part. On that note, so what I'll be sharing today is some work which is joint work with Elliot Young and Christa Gal, who are also at UMass Amherst. And this work is very much motivated by the research that Neve mentioned that I'm doing in the area of estimating demographic and health indicators. So there is this trend, this recent development that a lot of complex models are being used to produce estimates for a whole bunch of indicators for a whole bunch of populations, also in settings where data is not necessarily there. So while maybe a lot of people are working on big data these days, I would actually say that I work with small data. I just work with big models. So to give you more of an insight, what I mean by that is an example model that I'll use here as an application for this paper, which is a Bayesian model to estimate unintended pregnancies and abortions for all countries in the world. So this is work that we did recently with Guttmacher and WHO, where we came up with this modeling approach to try to estimate these important indicators where data is not always there. And this model itself, I can talk about it for hours, but I only have 40 minutes. So what I'll do in the interest of this talk is give you just a simplified summary. So what is this simplified summary? So we refer to this model as a Bayesian accounting model. And the accounting part comes in from using in the background, basically a demographic equation that makes sure that when we compare women to pregnancies and birth outcomes, that things match up, that these things are in balance. So that's where the accounting comes from. So to briefly summarize then this accounting setup. So looking at this diagram here and focusing on the first bullet point, basically what we do accounting wise is for each country and 5-year period, we start on the left with thinking about women being divided in different subgroups based on their union and family planning status. For example, there are married women who would like to have a child, there are married women who use contraceptives, and there are married women who say they don't want to have a child, but they're not using contraceptives either. So with an unmet need for contraceptives. Then going from the left to the right, you can obtain the pregnancies associated with each subgroup of women if you would know this subgroup specific pregnancy rate omega. Then going from pregnancies all the way to the right-hand side to our outcomes of interest, well, if we would know what is the propensity to abort unintended pregnancies, which are associated with the subgroups of women who say that they don't want a child now or within the next 2 years. If we know the propensity to abort these unintended pregnancies, then we can come to the right-hand side of our little accounting diagram, which is we can figure out how many intended births, how many unintended births, and how many abortions there are for that country period. So that's basically the accounting setup. Now, in order to come up with estimates of especially the things on the right-hand side, so intended births, unintended births, and abortions, what do we have to do? Well, we would have to try to fit this accounting model to whatever data we have available. So what data we have available is as follows. So for all country periods, we don't actually have data, but we have estimates with uncertainty that are telling us what is the number of women in each subgroup. So those are estimates that Neve herself works on. As well as on the right-hand side, we have estimates of the total number of births for a country period. So those are the things we have for all country periods, so that's good news. Then what else do we have? Well, we also have some data on births by attention data or marital status, and we have some data on abortion, but we only have it for a subset of country periods. So to illustrate to give you a sense of how countries vary in terms of their data availability, I'm going to give you 2 examples. So this is an illustration of the data of that are available related to abortion in a high-income country. So these estimates, they went through country consultation, but they have not yet been published. So I cannot give the name of the country. That's why I just call it a high income country, but it is a true country and it is like real data. I'm not making things up here. So looking at this high income country then, what you see in the plot on the y-axis, I have abortion rate. So the number of abortions per 1,000 women of reproductive age. On the x-axis, I have time. And then these colored dots here in blue are observations from abortion studies, which are available for all these years here. And then what's given here in yellow are official statistics, which are known to underreport abortion because they don't capture all abortions. So these are being used in our model as a minimum. That's why you have the little triangle, while these studies, they're deemed to be complete. So these are used as point estimates. So given those data then, can we estimate abortion rate over time in this particular country? Yes, we can. So what you see here in the background in those gray lines are the abortion estimates with uncertainty associated with it, which we estimate for every 5-year period. So that's an example of a high income country. Now here's a second example. So this is the same idea. So abortion rate plotted over time, but in this middle income country, MIC, we only have 1 study in 2012 associated with abortion. Now, that's indeed a subset of periods only. So that's, of course, so now we're in a more data limited setting. Now, the good news for this country is there is data available that's on related indicators. So here I have the percent of births that were unintended and the percent of intended births that were to married women. And so here we have different data and different ranges that can inform basically what is going on when you think back about this simplified accounting framework to try to estimate abortion and related outcomes. But it doesn't directly give us information about abortions. But as you see here in gray, we do come up with these model-based estimates of abortions. So how do those come about? So that then leads to a little bit more detail on this Bayesian accounting model. So to produce estimates for all country years for all our indicators of interest, we make use of Bayesian hierarchical time series models, and we put those on our unknown parameters. So thinking back about the diagram, we need to know the subgroup specific pregnancy rates, and we need to know the propensity to abort unintended pregnancies. So we're using Bayesian hierarchical time series models for those so that we can exchange information across time periods within a country period, but also across regions within the same, across countries within the same region. So to give an example of a hierarchical time series model that we use for some of the pregnancy rates, the thetas, for country C, period T, and subgroup S, we assume a random walk with region-specific drift. So this equation here is saying that for this parameter at time t, my best guess is the parameter at time t minus 1. But then what I add to it is this delta term here, which is the change that we have estimated for the region RC that country belongs to. So you can imagine what happens then is even if you don't have data, if in the region you have data on other countries and it shows like an increase or a decrease, that information then is pulled in when we try to obtain estimates for this, this country of interest. Now, back to this little plot then. So, wow, the good news is we only have one data point on abortion, 2012. We have some data on related indicators. We have these hierarchical models in the background. So yes, we can produce these estimates of abortion over time. So now my question to the audience is, hooray or nay or hey, is this a good thing or a bad thing that we can produce those estimates? And I'm used to, I've been complaining about Teams to Neve now for the last week or so. I'm more used to Zoom. Like, is there like a Zoom thing you can do like, oh, smiley face, oh, frowny face?
You can put, there's no frowny face, there's just smiley faces.
Oh, okay.
So you're going to get a
well, okay, so show me a smiley face when you think, oh, this is a good thing. And don't do anything when you think it's a bad thing. I see at least 2 smiley faces. Oh, where is she? Okay, so I see well, what I expect to see actually. So this is an audience of statisticians. So everybody's like, yeah, you can estimate something. That's awesome. And you're using like a nice fancy model, call it, give it a nice name. You're done. So I agree with that to some extent. I agree with that a lot. But over time, as I've seen. As I've gotten a little bit more into how these estimates are being used by others, I got a little bit more concerned. So my concern is related to this following point. So if model-based estimates are to be used for programming or policy making, then maybe we want to give users a little bit more than just a point estimate at a credible interval. So the reasoning here is that as far as I understand, it's really hard for users to actually use credible intervals, so people look at the point estimates. And as soon as you come up with a nice model to produce point estimates, there is a real concern that these estimates coming from the model are just treated as the truth. Like, oh yeah, we know what's going on in this country. And we can then form our policies and programming just based on that, which is not true, right? Because there's like a lot of inference taking place, a lot of assumptions being made. So to make this concern and what we try to do about it a little bit more specific, I want to introduce some notation to talk about how model-based estimates come about, how to think about that. So here, in terms of notation, for the rest of the talk, I'll refer to mu as my parameter of interest. So when you keep this Bayesian accounting model in the back of your mind as an application, mu can refer to the change in abortion rates in that middle-income country from the very first period to the last period. And then I'm going to refer to y as one or more data points.
Just hold on, something weird has happened. Has someone else like shared their screen?
Yeah. Oh.
Okay, let's Joe, is it? Joe, I can't unshare somebody's screen. I don't even know how that happened. Does anybody know who Joe is so we can get in touch with him to ask him to stop sharing his screen? Okay, Leontine, you want to share your screen again?
I just shared my screen and then cancelled it, so that.
Okay, thanks. Okay, let's keep going. Thank you. I have never seen that happen before. Sorry.
Sure. Okay. So yeah, so I was introducing some notation to talk about how model-based estimates come about. So mu is the parameter of interest, and then I'm going to refer to y as the data for the relevant country for the the country period that's associated with that parameter of interest. So if our example is that mu refers to the change in abortion rates in the middle income country, then Y could refer to either just abortion data, or what we're going to focus on here is any data in that middle income country related to the outcome of interest over time. And then Z here refers to any other data. So in the context of our Bayesian model, that means that's the global database with data from all the countries except for that middle income country. So with this notation, how can you think about model-based estimates? How do they come about? Well, you can think about model-based estimates as coming about as being produced by some posterior distribution, P mu, given all the data, so Y and Z, where just using Bayes' rule, this posterior then is the combination of what I refer to as a model-based prior, so P mu given Z, as well as the information coming from this additional data Y, which I'll Py given mu and Z, which I'll talk about in terms of its normalized version, so the normalized likelihood function Q of mu. What's here on the slide on the right is just a diagram to give you some illustrations of different ways in which this posterior that I always plot here in black comes about from combining this model-based prior in red and the likelihoods function coming from the data Y in green. So starting with the top left point here, you see that the posterior in black is really driven by the data, by the likelihood function in green. Going from the top left to the bottom left, we see that here the opposite is going on, right? We see that the posterior now is driven by the prior as opposed to this additional data for the country period of interest. And going from left to right, we see some different effect going on. We see, for example, in the top row, that yes, the posterior is still driven by the data of interest, but now we see that the prior actually is more aligned with the data, as compared to this this last point here in the lower right corner, where as compared to this this plot on the left hand side, where the prior and the prior and the data are basically telling a different story about the outcome of interest. So this is an illustration of different settings, different ways in which the posterior can come about. So why am I showing you this? Now, well, let's step back and let's think about what we provide to a user of model-based estimates. The only thing we provide to a user of model-based estimate is basically the posterior in black. We can give it the posterior in black. Do we tell it anything associated with which setting we're in for that specific indicator, whether it's like driven by the data or not driven by the data, whether the model-based prior aligns with the data or not? We don't, right? So that's the motivation for our talk. Basically, what we aim to do in this work is to come up with new measures to complement any model-based estimates that we produce. These new measures are, we propose to come up with two measures to basically capture those different dimensions of the illustration I just gave you. So the first measure that we propose to come up with is a data weight, small w, which should be a standardized measure between 0 and 1 that captures how much a model-based estimate is informed by data for the relevant population period versus information from other populations and periods and model assumptions. So basically what I have here now on the vertical axis, on the y-axis, is the data weight measure. So if we can come up with this measure, W, then basically that measure should be 0 in the bottom row, and it should be 1 in the top row, as we see that the model-based estimates are more and more driven by the data going from the bottom to the top. Then similarly, we're also interested in coming up with a second measure, a data model accordance measure, small a, to quantify how extreme the data are as compared to the model-based prediction. And what does that measure capture? So that measure captures the x-axis, where going from the left to the right, on the left-hand side, the accordance is close to 0. The data and the model-based prior are not well lined up, while on the right-hand side, they are well lined up. Now, if we would have both these measures, basically what we can do, how we can use these measures is give them with every model-based estimate. So that basically then you can put these model-based estimates in different quadrants. In the first quadrant here in the top left, well, basically here we see that the estimates are data-driven, and the data suggests something different than what's expected under the model. So this could be like an interesting case study quadrant. Then the top right is same thing. So estimate is data driven, but here it's not so much maybe of interest as a case study because the estimate is as expected under the model. And then the bottom row here is where things get a little trickier. So starting with the bottom right here, well, we don't have that much data. We have a low data weight, but we also don't have strong evidence of a data model conflict. Now, the more worrisome one then is the last quadrant in red. Here, we don't have any data, and the data that we do have suggests something different from what the model-based prior suggests and what our model-based estimate looks like. So this is definitely a setting then where, yes, we have a model-based estimate, but actually we would want to advise a user to collect more data to actually understand what's going on. So going back to the big picture of my talk then, so basically what I just introduced is a background to motivate our aim, which is to propose measures to complement model-based estimates. So then the next part, next little section is going to be on the approach. So I'm going to define our proposed data weight and data model accordant measures and do so based on a mixture of normals. And then I'll come back to the application at the end. So actually calculate these measures for the abortion estimates in the middle income country. Okay. So what's the approach? What do we propose in terms of the measures? How we started thinking about the measures was very much informed thinking about what if I have a normal prior and I have a normal likelihood function? How would I want to propose these measures? Which that was relatively straightforward. And then we got into like dozens of rabbit holes for too long when we tried to generalize from this simple normal setting to something that we can use in any setting. But eventually we came out of all these rabbit holes, and we realized that we can generalize these measures that we had in mind by thinking about approximating the model-based prior and the normalized likelihood using mixtures of normals. So I'm going to present this setup and as well as the measures to then give some intuition for it. So what is this setup? So introducing again some notation here. So we're going to assume that we can approximate the prior and the normalized likelihood by some finite mixture of normals. So in terms of notation, we assume we have capital J components in the model-based prior. The pi's refer to these component specific weights, and then I have a mixture of normals. So this phi here refers to a normal probability density function with parameters being the prior, specific, mean, and variance. And then similarly, we also assume that the normalized likelihood is this mixture of normals with its own weights and its own mean and variance parameters. Well, in this setup, when you combine a mixture on a prior and a mixture on normalized likelihood, then your posterior becomes a mixture of normals as well. So maybe it helps to have a little visualization in your head. So in this illustration here, what I have in these three graphs is, again, prior in red, normalized likelihood in green, and posterior in black. So in each of these graphs now, the prior in red is just a standard normal to give it an easy start. But then what I added in green is the normalized likelihood, which in the first example is just a standard normal as well. But then in the second and the third example, the normalized likelihood is a mixture of two normals. So in each of the three settings, it turns out that these posteriors that you see here in black, they themselves can also be written as mixtures of normals. And to obtain the parameters of those mixtures, those details are on this slide. So this slide looks horrible because it has too many Greek letters, but actually it's not that scary at all. And it's pretty straightforward when you actually work out the details. So what's this posterior mixture boils down to is it becomes a sum over the likelihood components and over the prior components of posterior weights and normal densities with the posterior means and variances based on the prior and the likelihood components. So then what are these expressions going into these different parameters? Well, it turns out that the mean becomes this, the mean for the jkth component becomes this weighted average of the prior mean of that component and the likelihood mean of that component, with the weights driven by the variance parameters that are given by the two components. And similarly, the variance itself is given by the variance components of the prior and the likelihood. And then last but not least, this posterior weight here for the jth component is driven by the weights that come from the prior and the likelihood for that component, as well as this integral, which here we labeled capital P. So this is integrating the product of the prior components and the likelihood components. I write it here as an integral to give some more insight, but actually this is available in closed form as well. So bottom line of this slide here, I get this posterior, which itself is a mixture of normals, and I can figure out the parameters. Now, why is that good news, or why was that a helpful, not a rabbit hole in our case? Well, because then based on this setup, we actually can come up with a data weight and an accordance for our purpose. So starting with the data weight here, so first as a reminder, so our goal was to come up with a data weight W that quantifies the weight given to the information from the data, so the normalized likelihood as compared to the model-based prior. And the weight that we came up with here is easiest understood if you go directly to this last expression, which is the posterior mean for mu given all the data including y. This posterior mean is this mixture setup turns out to be this weighted average between prior means as well as likelihood means. So what do we set our data weight equal to? We set the data weight equal to the total sum of the weights associated with the likelihood means. If we define the weight as such, then the interpretation is that W is the total weight assigned to the means of the normalized likelihood. So it's basically saying, let's restart this sentence. So basically this W as defined the way we do, it ranges between 0 and 1, where a weight equals to 0 means that no, in determining the posterior mean, all the information comes from the prior. Well, if W is equal to 1, it means that all the information in terms of determining the posterior mean comes from the likelihood, which indeed aligns with our goal. Now to get some illustration of this, so that you don't have to just take my word for it. So I find this easiest understood, as I mentioned earlier, thinking not about a mixture setup, but thinking about combining just like a one component prior with a one component likelihood setup. So what I have here in the plot and what I'll talk you through on the slide is the setting where the prior is just one component. So say the prior is a standard normal as an example, and the likelihood is also one component. So think about just having observed one data point, y, that relates to mu by being a normal centered at mu. So that results in the normalized likelihood being a one component normal. Then when you work out the expression for the posterior mean in this setting, it's directly the weighted mean of the observation y as well as the prior mean. So indeed, it's the weight given to the data as compared to the prior mean, which is a nice simpler expression. And also then when you look at these illustrations here, hopefully it makes a bit of sense. So the prior, the standard normal, again, in all the three plots is unmet. So what I added here are different examples of the normalized likelihood. So this normalized likelihood is centered a little bit to the left of the center of the standard normal of the model-based prior. And what I arrange here going from right to left are the variances. So starting here in the middle, the variance is equal to 1. So here the variance of the model-based prior and the likelihood are the same. So we see here that this posterior becomes basically this equally weighted combination of the prior and the likelihood, right? So then finding out that the weight is equal to a half is something that you would indeed hope for or expect or want. And then similarly, when you increase the variance, well, when you increase the variance, the posterior becomes more driven by the prior. So then we see that the weight decreases, in this case to 0.2 when the variance is equal to 4. And then similarly, when you decrease the variance in your likelihood, the weight increases to 0.8. So that's an illustration for a simple normal case. And then the second illustration here is when you actually use a mixture for the normalized likelihood. So here in red, the prior is still the same. It's just your standard normal. But now, and then the plot here in the middle is the same too, where I still have this one component normalized likelihoods with a weight of a half. But then what I do going from the middle plot to the most left plot is instead of having just this one component with a variance of 1, I now have 2 components, where in 1 I increase the variance to 2. Well, if you increase the variance in one component, then what you see is that the data weight decreases, as you would want to expect. And then similarly, going from the middle to the right-hand side, or maybe I set the direction the wrong way around in my first talking tree. But so going from the middle plot to the right-hand side, I decrease the variance in one of the components. So I see that the posterior is more driven by the data, by the likelihood. So I see that the weight increases. I'm doing quick pauses and checking in on my second screen, but I don't see any chats or problems showing up. Okay. So then moving on to the second measure, which was this accordance measure. So as a reminder of the goal, we want this data model accordance measure A to quantify how extreme the data are as compared to the model-based predictions. Basically to check whether or not the data are aligned with what we with what we are assuming based on the model and other data. Then again, on this slide, I have a definition and interpretation, but actually I want to start by this last bullet point here, because again, I find this measure easiest to understand starting from a simple normal one component place. So the example here is I have one component for the likelihood and for the prior. And again, my likelihood think about as observing one observation Y that is derived from a normal step. Centered at mu with a variance of sigma squared, Then how we define this accordance measure in this just one component normal case is the prior probability of mu being more extreme than this one data point Y that we have observed, which is illustrated in this diagram here. So what you see here in green is the normalized likelihood again. In red, you see the prior. So how do we define the accordance in this simple setting? We define the accordance by checking, oh, where does the mean of my likelihood function fall in my prior? And then calculating basically the tail areas based on where the mean falls. So here the mean falls in the more extreme tails of my prior. So my red area under the curve, the accordance is equal to 0.1. In the middle, it's equal to 0.5. And then here on the right-hand side, we see that the mean, the likelihood mean, as well as the prior mean overlap. So then the prior probability of mu being more extreme than Y is equal to 1. So they are in complete accordance as compared to they are not in accordance on the left-hand side. So that's this is the main idea. If that's all you want to get out of this slide, I would be happy already. But if you want to then know the details on how we extended it to the mixture of normals, those are then defined on the slide as well. So what we did for the mixture setup is extended such that our total accordance in a mixture setup becomes this weighted sum of component-specific accordances, where the component-specific accordances are basically you compare likelihood component K with prior component J, and you do exactly what we did here for just the one component normal case. So you calculate these component-specific accordances, and then you sum them up and you weight them by the relative importance of the likelihood and prior components. Now, why do you need to weight them by their relative importance? We played around with that as well. But when you do impose that weighting, you get results that are aligned with our goals. And that's illustrated, or there's one illustration of that on this slide. So starting with the plot on the right-hand side, as before in red, the prior is a standard normal. And now in green, this normalized likelihood is the mixture of those two normals with different variances, but they are both centered at 0, just like the prior. So what do you get here in terms of your accordance? You get an accordance of 1, like the data are very likely under the prior. Now go to the right-hand side. So this is an illustration of a setting with an accordance of 0. What is this setting? Well, here, this normalized likelihood is bimodal because it has a mean at -2 and it has a mean at 2. So then when you check, oh, how likely are these data under the prior? Well, both of these modes, both of these means, they actually fall in the tail area of the prior. So indeed, the accordance is low. In this case, it boils down to 0. Okay, so I now introduced our measures. So just to summarize or come back to the big picture, basically what we want is when we give users a posterior distribution, so distribution here in black, we want to give those users also 2 measures. A data weight measure so that you can distinguish between bottom row and top row, as well as a data model accordance measure so that you can distinguish between likelihood and prior being aligned versus being not aligned. So then the last part is coming back to our case study. So remember this set of abortion estimates that we had for the middle income country, where we had 1 data point on abortion rate, and then we had some data on associated indicators. But we also had these hierarchical models working in the background, which says that, oh, these abortion rate estimates in this middle income country are informed by whatever trends are going on in neighboring countries. Now, let's make specific what indicator may be of interest. So let's say that mu here, our indicator of interest, is the change in abortion rate from the very first period to the last period. So if a change is positive, it means there was an increase, and if the change is negative, it means there was a decrease. So based on our model and based on our model-based estimates, we can give any user an estimate and a CI for this outcome. But then the question is, oh, but now let's give some more insight. So what is the data weight and the data accordance associated with that outcome if I consider my data set Y to be all the data available in the middle income country? So what if, another way to think about it is like, what if I wouldn't have this 1 abortion study and these other data points here, then how different would my estimate be? And also, to what extent have I updated my estimate based on actually having observed this data Y? So that's a goal. The approach that we took, we could have taken an approach where, given our goal, we would have come up with a very specialized calculation to get the outcomes for our abortion case study. But that's not the route we went based on how we motivated this work. The route we went was to try to come up with a very simple approach to calculate the measures, basically for any set of model-based estimates of interest. And the rationale to try to come up with a simple approach is that we hope that measures like the ones we're proposing can be included in what we think are important initiatives. So one of them is Gather, which basically, if you're familiar with Prisma for systematic reviews, like these guidelines to actually do research. So similarly, Gather are this set of guidelines that give reporting standards for model-based estimates. So thinking about guidelines, like how should people report their model-based estimates? Well, ideally, we would like measures like the one we're proposing to be added to it. But of course, to make that possible, we do need to come up with a way to actually get these measures for any model that a modeler may be fitting to make this plausible and realistic. So what do we settle on in terms of making this possible? Well, we settled on, in terms of making this possible, by just assuming that what we have are samples from the model-based prior and samples from the posterior distribution. we think it's realistic to think that a modeler can obtain those because what it boils down in practice is the posterior you already have, right? You fitted your model to all the data you have to get the posterior. Well, then can you also get this model-based prior? Yeah, sure. Just fit the model that you have to all the data, leaving out this data Y. So that's illustrated here for the abortion example. So what you see here in black now is the posterior distribution for our outcome of interest mu, this change in abortion rate in the middle income country, using all the data. And now what we added here in red is the model-based prior, which we get by, again, fitting our model to all the data we have, except for the data in the middle income country itself. Yeah, so this is our starting point. Instead of saying, oh, specifically what is going on in the background in the abortion model, we just say, hey, this is our posterior for an outcome of interest. And if we leave out data Y, this is our prior for the outcome of interest. Now, based on these samples of the posterior and the prior, the question is, can we still calculate the data weight and the data model accordance? And so the good answer is yes, or it's somewhat ongoing, but it is yes eventually. So the answer is yes, because we do have a clearly defined setup. What is our clearly defined setup? Well, if we have observed samples from our model-based priors, so mu I prior is a sample from our model-based prior, and we have observed samples from our posterior, then and we have assumed that the prior is this mixture of normals, and then this posterior is this mixture of normals that follow from the prior mixture of normals and the normalized likelihood mixture of normals. Then we have a valid estimation problem where we say, okay, we have these samples from these two densities. So what we need to estimate is the underlying parameters, the parameters underlying those two densities. So what we need to do is we need to estimate how many components do we have in the likelihood and the prior, and what are these parameters. And as I mentioned, so this is an ongoing work. We've gone two routes with this so far. So one way to solve this computation problem is to say, let's think about these finite mixtures as basically arising from Dirichlet process mixture model, so arising from an infinite mixture setup. So that's one approach. The other approach is to just say, okay, this we're gonna do the fitting, assuming we're working with a finite mixture model. So, for example, the very much Irish driven MC class R package uses an EM algorithm to try to estimate the number. Try to fit a mixture of normals to some data observed, and then it uses, well, I can do different things, but for example, we use BIC to try to estimate the number of components. So those are the two routes basically that we've been working on. So with the main goal being, okay, given that we have samples from the prior and the posterior, how do we go about estimating these underlying mixtures?
So we have about 2 minutes left, Leontine, so we have time for questions.
Okay, so yeah, then okay, so then I'll actually I'll skip over this. Basically, what I'm going to show you then are the results that are based on a simplified approach to this computation right now. So this is the high income country where, remember, it basically had data on abortion rate for every year of interest. So what do we see here as a reminder of notation? So the prior samples here are in red, the posterior samples are in black. And now these lines that are being added are mixture approximations to the prior and the posterior, as well as the likelihoods that we estimate to be associated with these samples. Now, in this case, the likelihood and the posterior overlap in this setting, as we would expect. The estimates are very much data-driven, so we get a data weight of 1 and we get a low accordance, because actually the change is more negative than what would have been expected under the model. So you can think about this setting as being a setting in the yellow, in the was it the yellow quadrants, where like it's an interesting case study. And then last but not least, so in terms of the middle income countries, so now again, we have samples of the prior and of the posterior, with the lines now being the mixture approximations that we estimate. Here we see that when we do the estimation, the likelihood here actually is more towards more positive change as what we find in our model-based prior and in our posterior. So what we find here is we have not only a data weight that's only 0.4, like there's a lot of information coming from other countries and model assumptions as compared to the country's own data, but also the accordance is quite low. So this actually is an example of a country that's in this red quadrant where, well, you better collect more data if this is really an outcome of interest. So this is basically the end of my talk, and now I just have some summary slides. Can I use 1 minute for that? Thank you. So what did I discuss right now? So the idea was that, oh, there are all these models out there to produce estimates for demographic indicators, but to really give the user a little bit more than just a point estimate and a CI, we proposed 2 new measures, a data weight and a data model accordance. We came up with these measures using mixtures of normals. A note here is that these work well for use with unconstrained support. In some ongoing/future work, we are also looking into alternative mixtures, so beta mixtures or gamma mixtures. Then in terms of the computation, so that is it's ongoing work for us to calculate the measures based on using samples from the model-based prior and from the posterior. The second question related to computation is, of course, how to get the model-based prior. So as I mentioned, oh, you can just fit the model again, leaving out the data set Y, so it throws CPUs at the problem. But of course, in some settings, this may get computationally expensive. So there may be possibilities there to approximate the model-based prior based on the full data fit. And then last but not least, what was driving this was the intended usage. So the idea would be that these measures complement model-based estimates. So for that, I think it would need a bit more guidance. For example, like, oh, what should be your choices of why this data to leave out? Could be country data in the last 5 years, all country data. But then with these measures in place and with some guidance on how to go about getting them, we hope they can be included in initiatives like the gather reporting standards. Last but not least, we haven't really looked into it yet, but it could also be that these measures, once we have them, could be considered for model diagnostics and comparison. And that's it. Again, thank you very much. And I look forward to your questions.
Thank you very much, Leontine. So do we have questions for Leontine? You can raise your hands